In this video, I want to take a look at another type of first order equation, which is called an exact equation. Now, exact equations, turns out, are ones that come from implicit differentiation. So let's recall what implicit differentiation was. You actually probably saw it both in Calc 1 and in Calc 3. But the best explanation of it, and what we're going to try to work backwards, is what you would have seen in a Calc 3 class. So here's what we're going to do. Let's take a look at, just remember what we did back in Calc 3. So suppose you had an equation that was not just y as some function of x, but you have x and y mixed together in a relation. So you can move everything over to one side, leave a constant over on the other side. Sometimes the constant is just 0, but whatever. I don't care if it's 0 or not, just some constant. You got an equation that looks like this. Some function of both x and y on the left-hand side of the equation equals a constant on the right. Now, remember what we did for implicit differentiation. We essentially said we're assuming y is some function of x. Okay, so this function of x and y is actually a function of x and another function of x, because y is a function of x. So capital F is just a function of x when we're thinking implicitly here. So if capital F is a function of x, then I can take its derivative with respect to x. Typically, with two variables, you need to be taking partial derivatives. But if you're thinking of it only as one variable, then it's a derivative. And the way we figure out how to do that derivative is using the chain rule. Remember how we did that? We thought of f as a function of x and y, and that x and y are both functions of x. X is a very simple function of x, it just equals x. And y is also a function of x, but that's what we don't know. We don't know, we're just assuming implicitly that y is a function of x. Okay. Now, in order to take the derivative of f with respect to x, we have to realize that changing x changes f in two different ways, because changing x changes x, which changes f, but changing x changes y, which also changes f. So there's a matter of the derivatives involved in all these branches. So f is a function, first of all, of two variables that has partial derivatives. And then these are both functions of one variable, so they both have just single derivatives. So when I talk about what's the derivative of f with respect to x, it has two parts. It has the part that goes on this branch, and it has the part that goes over here on that branch. So that first branch is the partial of f with respect to x times dx dx, and then the other branch over here is the partial of f with respect to y times dy dx. This is one of the forms of the chain rule for multivariables. All right, this is a y here. Now, let's switch back to the computer screen. And here's what we do, right? We've got this equation. I'm taking the derivative of both sides with respect to x. The right-hand side is really easy. The derivative of that constant is 0. The derivative of the left-hand side is what we just figured out, the derivative of f with respect to x. So there's the partial of f with respect to x times dx dx plus the partial of f with respect to y times dy dx. Now, this simplifies a little because dx dx is, of course, just 1. The derivative of x with respect to x is 1. And so that just goes away. That's a 1. And then I'm just using different notation, using the subscript notation, f sub x to mean the partial with respect to x, and f sub y is the partial of f with respect to y. Now, doing implicit differentiation, we then would say, okay, I need to solve for dy dx, and so you subtract the f of x over f sub x over to the other side, and then divide by the f sub y. Okay. And dy dx is minus the partial of that function f with respect to x, and divided by the partial of f with respect to y. I have to admit that when I was learning implicit differentiation in Calc 1, I felt like I was doing the same thing every time. Every single problem was the same. And then you get to Calc 3, and it turns out that, yeah, in fact, it is all the same, because every time you end up with the same answer. You end up with whatever this thing is, whatever this function is, take the partial with respect to x, stick it in the numerator with a minus sign, take the partial with respect to y, stick it in the denominator with a plus sign, and that's what dy dx is. Okay. So that's the process of implicit differentiation. Our job today is to reverse it, try to go the other way. But notice, this right here just looks like a first order differential equation. dy dx is some function of x and y. Since capital F was a function of x and y, its partial derivative will be a function of x and y. And the partial derivative, both with respect to x and y, they're both functions of x and y. So this just looks like a first order differential equation. And so I've got three questions. One is every first order equation exact? That is, because this, no matter what you have over here, you can think of it as a fraction, if nothing else, the whole thing you've got divided by 1. Is it exact? If it's not exact, if not everything is exact, how do we know what is and what isn't? How do we know when what we're about to do will apply? And third is, what is it we're about to do? Can we actually solve, if we decide this does come from implicit differentiation, can we work it backwards? And so here we go. Three answers to those three questions. One is, of course, no. Not everything is exact. How do we know? There's this thing called Clairaut's theorem, although I've also seen it called Schwarz's theorem. And the answer is yes, we can do this backwards once we know that we are in the situation that we want. Okay, so the notion of exact is if we can recognize that the equation, the first order equation that we have, came from implicit differentiation, then we say that's an exact equation, and then we're going to be able to solve. That is, we're going to be able to work our way back up to something that looks like this, some function of x and y equals a constant. Okay. So, first of all, you might say, Clairaut's theorem, what the heck is Clairaut's theorem? Well, let me remind you from Calc 3, we had this. Clairaut's theorem was that if you have a function of x and y, and you take its second mixed partials, so you take the partial with respect to x and then y, or if you take the partial with respect to y and then x, that you get equal results under certain circumstances. So if those second partial derivatives are continuous functions, then they will be equal to each other. Okay. So if we've got a differential equation that looks like this, dy dx is equal to some function of x and y over some other function of x and y, and I'm just choosing to call the numerator negative my and the denominator n of xy, because of what I'm about to do, but it's just, you got one function divided by another function, and we got something like that. We want to check to see if we could have gotten it from implicit differentiation. So I'm going to try to get it to look like this thing right here. Okay. So what I'm going to do is I'm going to multiply both sides by that denominator n, and then add the m to the other side. So I end up with this, mxy plus nxy dy dx equals 0. This is quite often how you will see these equations written, not in this form, but more in this form. Sometimes they even go as far as to multiply both sides by dx and write it this way, say mx dx plus mxy dx plus n of xy dy equals 0, right? That just multiplying both sides by dx gives you this. Either way, right? I'm looking at this form right here saying I want it to look like this, that if this came from implicit differentiation, I know that this is the first thing I get when that implicit differentiation happens. And so this is looking like the m is sitting in the spot where fx should be, and the n is sitting in the spot where f sub y should be. So if it did come from implicit differentiation, I need m to equal the partial of f with respect to x, and I need n to equal the partial of f with respect to y for some unknown f. This is what I then need to find, is what f is. But first I need to just see, could this possibly be true? And this is where Clairaut comes in, because if this m is the partial with respect to x of some unknown f, then take its partial with respect to y to get the mixed partial fxy. Likewise, if n is the partial of f with respect to y, then take its partial with respect to x to get fyx. And if there is such a function f, which makes n equal to this and m equal to that, then it must be that this mixed partial fxy is this mixed partial fyx. So we have to check, is the partial of m with respect to y equal to the partial of n with respect to x? If it's true, then yes, there is an f for which this works. If that's not true, if they're not equal to each other, then no, then it doesn't. Let's show you a couple of examples here. Here is a differential equation, dy dx equals this over that. And so I'm going to multiply both sides by that denominator and move this over like before. So this is the m, the 2x plus y is m, and the 2x plus 3y squared is n. If I take the partial of m with respect to y, because this is in the role, sitting in the spot where there should be f, partial of f with respect to x. So take it with respect to y, partial with respect to y, x is a constant when I'm doing partial derivatives. So that's just 2. And then n is sitting in the spot where this should be f sub y. So take its partial with respect to x. Well, the partial with respect to x here, y is a constant, so that's just 2. And sure, both of them are 2. This is an exact equation. Okay, we will be able to find the f that it came from. In fact, that's going to be the first example that I do in the next video, right, as I'll do this one. Let me just show you an example where it doesn't work. So, for instance, here, very close to the same as this one, but what did I do? I changed that 2 to a 3. So what that did was m is the same as it was before, but n is now 3x plus 3y squared. And take the partial of this one with respect to y, you get that 2. Take the partial of this one with respect to x, you get that 3. 2 is not equal to 3, so this is not an exact equation, and we would not expect to be able to find the f that would be the solution. Okay. So the next thing I need to do is actually do some examples of how we solve these equations once we've decided that they are exact, and I will do that in the next video.